Today we're going to talk about equilibrium systems. Chemical equilibrium is a state in which the rate of the forward reaction and the rate of a reverse reaction in a system are equal. Okay, now, first of all, we've got to know what we're talking about when we talk about forward and reverse reactions. Let's say we have a situation where A and B are reacting to form C and D. There are circumstances when C and D, when this reaction will be what we call a completion reaction. This is something we call a completion arrow, meaning A and B completely react to form C and D. This generally happens when C or D are possibly a gas or a precipitate, and they leave the reaction system, if you will. If it's a precipitate, it would sink down to the bottom. It would no longer be present to continue reacting. If it were a gas, for instance, it would bubble off of the system and no longer be present for reacting. Because what sometimes happens is that we'll have a situation where once we form some C and D will start colliding with each other, and they will react in reverse, go back to form some A and B. So in this situation where you have A and B reacting to form C and D turning right back around and reacting to form A and B, you have what we call an equilibrium situation. You have a forward and a reverse reaction occurring, and when they are occurring at the same rate and that rate is no longer changing, then we have an equilibrium system. So I think you can see now perhaps that if you had some D and it was a gas and it disappeared, well, disappear meaning bubbled out of the system, then it would no longer be present to collide with C and you couldn't get any reverse reaction. The same situation would happen if, for instance, C were a precipitate. If it precipitated out, it would no longer be present in the system or available to collide with D and react in reverse to form A and B again. So those are the types of situations that occur when you have a completion reaction. This situation here with the forward and reverse arrows is an equilibrium reaction. And we can see this if we kind of move back through our notes a few pages. You can see a reaction here, and I've labeled it so that you can see where the products are starting out at 0 and the reactants are starting out at assumed 1 molar concentration. And as the reaction proceeds, you can see that the reactants are decreasing while the products are increasing. Now they're going to reach this point that I've labeled where the rate is no longer changing. Once that rate is, or I say the rate is not changing, they're continuing to react, but the rates of the forward and the reverse reactions are the same. And once those rates are the same, then we have an equilibrium situation. So you would say in this situation that equilibrium was established at 60 minutes or 60 seconds in this term. So going back here, let's look at how we can express that. We can use something called an equilibrium expression to show what how the equilibrium how the concentrations of each of the substances are affecting each other in an equilibrium situation. When we look at equilibrium constants, K sub EQ is the constant, is a value which we can use for any equilibrium system. We usually don't use units, so that'll be comforting after our whole rate law discussion and our K decay constant. So Kc, sometimes we write that, though we get more specific and say, okay, this is the equilibrium constant and with respect to concentration. Kp, the equilibrium constant in terms of pressure. We can say Ka, which is the equilibrium constant in terms of an acid. Kb, equilibrium constant in terms of a base, when we're dealing with a base. So there are lots of different specific Ks we can have. Again, Keq refers to all of them. Okay, so let's look at this particular reaction here where we've got some amount of A reacting with some amount of B, and it's an equilibrium reaction. Now, the only way I can get my arrows to work like this is to draw an arrow that has two ends. Please make sure that when you handwrite them, especially on the AP test, that you do the double arrows. Generally, they're drawn like this, just a little bit quicker than making a full arrow. But I've had some people tell me on the AP, some of the higher up AP people, that they do not accept something that looks like this on the AP test. Not exactly sure why, but they don't. So anyway, so you've got this reaction, and now we can write an expression for that reaction, and that expression in terms of concentration would look like this, where you've got products over reactants. So the K value is always going to be the concentration of the products over the concentration of the reactants in terms of concentration or pressure, whatever it is that you're dealing with. So in this particular case, since these are the products, these are the reactants, we're going to have the concentration of C raised to its coefficient, Y, times very important that it's times the concentration of D raised to its coefficient. We're going to divide that by, okay, we had a little bit of an interruption, but let's continue. So we've got now the, as we said, we're going to divide by the reactants. So we're going to put whatever the concentration of reactant A is raised to its exponent, W, whatever the concentration of B is raised to its exponent, which is X in the problem. And again, please, please, please make sure that you realize that these are both multiplied in between here, not added. They are multiplied. So watch for that. Now, once you know what the equilibrium constant value is, the numerical value, you can find other related values in this way. If you have and these are equations that you can use. If you have a reverse reaction, if this is, you've got a certain value for Kc for a particular reaction. If you reverse the reaction and you write that C and D are reacting to form A and B, then all you would need to do is to flip this. Products over reactants. So the reverse reaction would simply be the reciprocal of the first value for K. You can also write it as that Kc prime, or the new Kc, is equal to the OKC to the -1. Either way, you're looking at the reciprocal of the original Kc. If the original reaction is multiplied by some value, for instance, everything's doubled, then you are simply going to raise the old Kc value to the power of that factor. For instance, if it was doubled, it would be the old Kc raised to the second power. If you tripled the reaction, it would be the old Kc raised to the third. If you halved the reaction, it would be Kc to the half, or the square root of Kc. So keep those values or keep those equations in mind. And now try to separate it from Hess's law. Remember, in Hess's law, if we reversed the reaction, we simply changed the sign. And if we multiplied the reaction, we simply multiplied by whatever that factor was. That's for heat, for thermo. In equilibrium, we reverse the reaction, we take the reciprocal, we multiply the reaction by some factor, we raise it to the power of that factor. So keep them different. Also, another thing that we did, remember in Hess's law, we added reaction. If we had reaction 1, reaction 2, and reaction 3, we had delta H values that we simply added up. Like a 3 there. and we simply added it up to get the total delta H. Well, when we're dealing with equilibrium constants, we don't add them, we multiply them. So the overall equilibrium constant is going to be each of the equilibrium constants given for each of the steps in the reaction, in the overall reaction, and they're going to all be multiplied together. So those are the equations you have to think about. Now, when pressure is used in an equilibrium expression, or for an equilibrium problem, then you're not going to be able to use concentrations anymore. You have to use partial pressures. So the pressure of C raised to the Y, the pressure of D raised to the Z, etc. So watch for that. Don't put in concentration terms when you're dealing with pressures. They do not like it on the AP test. Also, when you're trying to relate concentration and pressure, equilibrium constants, Kc and Kp are the same if the number of moles of the gaseous reactant and the number of moles of the gaseous product are equal. That is the only time you have Kc equal to Kp. Otherwise, this is the equation you use, that Kp is equal to Kc times RT raised to the delta N. And delta N is the number of moles of gaseous product minus the number of moles of gaseous reactant. And I know I'm throwing tons of equations at you right now. We're going to do examples for each of these in just a moment, but I want you to have all the equations and all the tools here on just a couple of pages so that you can find them pretty quickly. Making another point, concentrations of pure solids and pure liquids are not included because they're considered to be constant. So pure solids and pure liquids are not included in the equilibrium expression. In addition, if K is greater than 1, then we would say that K favors the products of the reaction. If K is less than 1, we would say that the equilibrium system favors the reactants. Think about why. If K is equal to products over reactants, and you have a large K, that means your products must be big. So if the products are larger, that means you have more products. We say it's favoring the products in the reaction. So if you've got A going to B, and you've got more products forming, more of B forming, we say that reaction is shifted to the right. However, if you have a situation where K is less than 1, think about it. If K is less than 1, then it must mean that R is bigger than the reactant concentration is bigger than the product concentration. So if the reactants are bigger, that means you'd have more A in this situation, and we would say that this reaction is shifted to the left. We've got more A. That's just terminology. It's something you have to memorize. If you've got more products, you say it's shifted right. If you have more reactants, you say it's shifted left. So how do you get an equilibrium expression? Products over reactants, and I'm going to do Kc. So Kc is going to be the concentration of the products over the reactants. The first thing you want to do is make sure that you're not dealing with any pure liquids or pure solids, because if you are, you need to X them out. So Kc for this would be the concentration of NO2 raised to the 4th times the concentration of H2O raised to the 6th. And now we're going to divide it by the reactants. The concentration of NH3 raised to the 4th times the concentration of O2 raised to the 7th. So that's how we would get an equilibrium expression for that reaction. Now watch it on this next one. Remember what I just said. The very first thing you want to do is go through and double check your substances and make sure that you don't have a solid or a liquid. In this case, you've got two substances that are solids. Those are going to be X'd out. They will not appear in the equilibrium expression. So the way we're going to write this is that Kc is equal to the concentration of CO2, there's nothing to multiply it by, and there's nothing to divide it by. It's simply the concentration of CO2. So that would be the equilibrium expression for this. Now, if we wanted this in terms of Kp, the difference would be that we couldn't use brackets. We would have to use the pressure of CO2 as in our expression rather than brackets. So now let's use some of this information to make some calculations. Okay, it says we have 3 moles of NaCl, 1 mole of NO, 2 moles of Cl2 mixed in a 10-liter flask. Guys, put a little smiley face around how big the flask is, because that's going to be incredibly important. You need to make sure that you're dealing with concentration and not with just moles. Has to be concentration, has to be molarity in equilibrium. That's an always true rule. Okay, so we've got, if that's true, then we can take each of these values we've got up here and divide them by 10 moles per liter to get their concentration. And that's what was done right here for us. Most of the time on AP questions, it won't be done for us. And we'll throw in that 3, that 1, and that 2 without thinking about it, and we'll get it wrong because it has to be in concentration. So always double check your flask to see how big it is before you start doing any of the problem. Now, it wants the value for K for this reaction, and it says that K, we're going to see that the system, since they're all gases, our equilibrium expression for this system is going to be the concentration of NO squared times the concentration of Cl2 divided by the concentration of NaCl. We plug those values in, 1.52 times 10 to the negative first. And I'm not even putting in units because units aren't used in equilibrium, which is a very nice thing, I have to admit. 3.9 times 10 to the negative first on the bottom. Oh, and I missed something on this. Did you notice what I did? I forgot to put that NaCl was squared, so watch that. You've got to pay attention. The NO is going to be squared, so make sure you do that. So our value for NO is 4.0 times 10 to the negative third. I kind of wrote them out of order here from what I did on my equilibrium expression, but looks like our NO, which is, again, 4.0 times 10 to the negative third is going to be squared, and our 3.9 times 10 to the negative first is squared. So be careful on that. I almost made the same mistake, and it's not, I have to admit, it's not a good idea to write this out of order. I'm going to do this for you so that maybe you won't make that same mistake. I'm going to put that Cl2 first, and I'm going to put the NO second so that it's in the same order as it is in the numbers over here that we filled in. Those are little things that on a test or on a pressure situation will mess you up badly if you're not careful. Okay, so this comes out with Kc being equal to 1.55 times 10 to the negative fifth. No units, remember. Yay! Now we want to calculate K for the reverse reaction. Remember, for the reverse reaction, our new K is going to be simply the reciprocal of our old K. So all we have to do is take 1 divided by our 1.55 times 10 to the negative fifth, and we get a value of 6.45 times 10 to the fourth for our new K. Now it wants us to calculate the value of K for this reaction, and notice it was 221 and now it's 442, which means we doubled this reaction. Remember what we do when we double the reaction. Our Kc, our new Kc, is going to be whatever our old Kc was raised to that factor, which in this case is going to be our 1.55 times 10 to the negative fifth raised to the second, which is going to give us a value of 2.40 times 10 to the negative 10th. So that's what happens if we double the reaction. Finally, if we want to calculate Kp, first of all, we need to look at our reaction. In our reaction, we've got 3 moles of product, but we've only got 2 moles of reactant. Are Kp and Kc equal? They are not, because the only way they're equal is those moles of gases are the same on both sides. So our 3 moles of gas on this side and our 2 moles of gas on the left-hand side do not equal. So we're going to have to do a calculation. Remember, the calculation equation is that Kp is equal to our Kc value times RT raised to the delta N. And remember, delta N is product minus reactant moles of gas. So in this case, 3 minus 2, 1 mole of gas for our N value. So Kp is going to be our 1.55 times 10 to the minus fifth times, now it's not going to make a difference in this one because as you see it's going to be raised to the first power, but it could make a very big difference if the N value were 2 or more, because we want to make sure we've got the quantity RT and not just T raised to that power. So R is 0, our 0.0821, it's our liter atmospheres per mole Kelvin value for R. Again, I'm not going to worry about using my units because they're not really involved in this. The temperature, if you remember from above, it told you that we were going to do this at 35 degrees. So our temperature must be in kelvins. 273 plus 35 is going to give us 308 kelvins. Not going to worry about units. And as we just stated over here, we're going to raise that to the first power. So when we multiply that all together, we get that Kp is equal to 3.92 times 10 to the negative fourth. No units on that value.